morning session. So we have the pleasure to have the second lecture of Alexis.
Thank you. So today we'll start speaking about local uniqueness for interlacements. But first, just a reminder of where we stopped. So we stopped with some estimates on the capacity of the range of a random walk. So -1, but you could remove the -1 here, as long as you inverse everything else, it would also be true. And there were 3 cases. There was dimension 3, where it's like 1 over the range of the walk, basically. In dimension 4, this was up to logs, 1 over the number of points. And in dimension larger than 5, this was really 1 over the number of points. And so actually, after discussing with Perla and Amin and Bruno, like okay, I guess this is the lower bound of capacity, so the upper bound. This is due to Raf and Sapochnikov in 18. But for the lower bound, or the upper bound of the capacity, actually it's not so clear if you can use just the tool that I was mentioning yesterday. It's a bit harder, but this was still proved by Acela, Shapira, and Susi. Okay, I mean the main difficulty is the dimension 4 game. The others are easy. And actually, there's been a lot of progress in recent years on this. How is exactly the capacity behaving? So, for instance, I mean this is older, but you have a law of large number for the capacity if D is larger than 5. So this is Jane away. And then there was a long time with where this topic was not studied, but I mean now we know much more. So for instance, now you know CLT, I mean LLN for D. And it's not really law of large number, it's a bit more complicated. I'm not going to go into the detail because, you know, basically you need to renormalize not by n, but by whatever you need to renormalize up there, right? And like especially in dimension 3, it's a bit more complicated. You have a random limit, but I'm not going to go too much into the detail. So it's like you have some papers by the same author as above. It's actually partially the same paper. You also have some work on the topic from Shang in 19. So another paper in dimension 4 in 19, some authors. And also from Bruno, dimension 5 from CLT. So, yeah. We now know much more about the exact behavior of the capacity in all dimensions. All right. So now I want to speak about, okay, now we know what is the typical behavior of the capacity. You could remove the -1, it's very typical up there. But now the question is large deviation bounds, in a sense. So actually, it's really easy to obtain like some rough estimate. You can just use the Markov property and the Markov inequality. To obtain the following bound on the capacity being much smaller than it should be. The capacity of the range. So let's say you look at the capacity of the range and you ask that it's smaller than t, where but t will be small typically than what it should be, so it's like square root of n is equal 3, n over log n if d equal 4, and n if d is larger than 5. And the result is that the probability that this capacity is much more than it should be, this decays as exponential minus t minus c. Okay, these are some constants for all t than c, and this is still Raf and Sapochnikov in the same paper. So why is that? Basically, okay, if you just want to show that this probability is smaller than, let's say, than a half, okay, simple bound, this is just a Markov inequality. Right? You use your upper bound on the expectation of the capacity minus 1, use your Markov inequality, this tells you that this is smaller than 1 over t, you take t small enough, this is smaller than 1. Okay? If you want to have an exponential or stretch exponential bound like here, you just need to use the Markov property and cut your walk into, let's say, in larger dimension, into 1 over t path of length tn. Okay, and they are all essentially independent naturally, but you can work around that. And each of your path of length tn has a probability now smaller than a half. Okay, to have this capacity, and just by a monotony of the capacity, you get, since they are all essentially dependent, you get exponential minus the number of paths. Okay, that you've cut your walk into, and this gives you directly this point. Yeah. It depends only on the dimension. Yeah. Probably you can, larger dimension, you can probably get 1 or something. Yeah. But I'll come back to what are the correct exponential decay. I mean, okay, I will not actually for this particular problem. So for this particular problem, you can look at the paper of Asela and Shapira. 20 for the larger than 5. To find more precise bound and also lower bounds, so really large deviation for this capacity. But what I will be actually interested in here is not so much the capacity of the range. I mean, this can be useful too, but what I will need to study random interlacement is not the range, but it's the walk until it exits a ball. What I mean by that is I take x bar r. This is the set of xk for k smaller than the heating time of like B0, let's say for instance, R complement. Okay, so I just run my walk until it exits for the first time my ball of size R. Okay, and then, well, you can get the same result as previously, or you can actually deduce a new result from the previous using the diffusivity of random walk. So, more precisely, what you can show is that the probability that the capacity of the walk until reaching distance r is much smaller than it should be. So what it should be, let's give it a name, let's call this f of r. Okay, and this still decays, stretch exponentially in t minus 1. So still for t small enough. And I mean, actually, it's probably true for t large, just because it's constant here, but it doesn't matter. And my f of r, what is it? So it is almost the same as I had here on the left-hand side, except, you know, at n, the walk has only reached distance square root of n. Okay, so I need, basically, by the time I reach distance r here, I am at time r square. Okay, so it's exactly the same as here, except you replace n by r square. So you get r in dimension 3, r square over log r in dimension 4 and just r squared in high dimension. Okay, and the proof is just the diffusivity of the walk. You say, okay, either my walk has run a time of order, let's say, square root of t r squared, and then I can just use this result, or the walk has taken much longer than it should be, and this also costs you an exponential term like that. Okay? Yeah? No, I mean, it's log r square, but I mean, this is just a factor of half. Yeah, it doesn't matter, because you can absorb it in the t, basically. All right. So this is the capacity estimate that we will need, or the range of the walk, actually. And maybe just a small remark on this. If you look at the probability like that an overwalk, okay, will hit my my walk x bar r here. This is of order the expectation of the capacity of my walk divided by r to the d minus 2. Why? Remember our heating formula here tells us that this is of the order, I mean, maybe this is more, right? Depending on what x is, this will change. But, so this is of order the sum of the equilibrium measure, I mean, this is equal to the sum of the equilibrium measure times the green function. And if here you take x at distance r, then the green function is typically of order 1 over r to the d minus 2, okay, for any between, because this one is also included in the both sides r, so the distance between x and any point here is of order r, right, so you get this r to the d minus 2 here, and then you have the sum of the equilibrium measure, this gives you the capacity, okay? So this is now just a constant if d equals 3, because the expectation of the capacity, I mean, as I said, you could remove the minus 1 up there, or here, right? This is of order r in dimension 3. Then in dimension 4, this is r squared over log r, this is r squared, so the r squared cancels, so you get like c over log r, if d equals 4. And in high dimension, this is r squared, this is now r to the d minus 2, so you get r to the 4 minus d. If d is absolute. Okay, oh, this is the order. Okay, and so here, this is, you recover, if you want, it's not the easiest way to see it, but you recover the fact that the dimension 4 is your critical dimension for the intersection of two random walks, right? In dimension 3, if I start two random walks in the same ball, then they will intersect each other with constant probability within this ball. In dimension 4, this will not be constant, you will lose a small log, okay? And in dimension 5, they will actually not quite unlikely intersect each other. So you get back this this result about the intersection of random walks. Question? So that's why the dimension 4 is the critical one for the capacity. It's because it's the critical one for the intersection of random walks. All right. So now let's turn to local uniqueness for random interlacement. So, what is this? So let's say I take a ball, okay, let's say square ball, for instance, and I run a random interlacement and I look at what's happening inside this ball, okay? So, remember, what does it mean, running a random interlacement? It means you have a Poissonian number of trajectories. The parameter of this Poisson variable is u times the capacity. So here, let's say if it's a ball of length r, you have like Poisson with parameter u r to the d minus 2, typically, trajectories, and they are all independent random walks, okay, doubly infinite random walks. So let's say, then I start them with the equilibrium measure, right? Let's say the first one starts here, and then end up here, and then maybe I have a second one which does something like that, but then I have a third one which does something. And that you can see there in this small 2D picture, which is not representative of what's happening in high dimension, obviously, is that, okay, if you run enough random walk, then they will start to intersect each other, okay, especially in low dimension. And basically the question of local uniqueness is there a unique connected component of random walks in my ball of radius r? So this is some kind of percolation question for those who are more familiar with that. For my random interlacement process. Okay, so here you have local uniqueness. So you have a small problem when you do that, is that typically this will not happen. Why? Because you can always have a random interlacement trajectory that starts here and immediately go and exit your ball and almost spend no time, and then it's not so likely that it will get connected with all the rest. Right? So this local uniqueness event will not happen. But what you can ask for is just a slightly different event, but which is still local, which is you now take a ball of size, let's say 3r. Yeah, I mean, this is more, okay, let me try to stay consistent with the notation I will introduce later. This is r, and this one, so it's a balls of radius r and 2r respectively. And you now just ask that all your walks, they may not be connected inside the ball of size r, but they will be connected inside the bigger ball of size 2r. So all the walks that hit r. Yeah, okay, so this one may be helping me here to make my set connected, and then the other ones I can now run them right until they exit here. Okay, and you might have, I mean, they are all doubly infinite. You might have some additional trajectories, but I don't consider them, right? You might have some trajectories that do something like that. And I mean, they can, I mean, okay, I can consider them. They can also help me if I want to connect my trajectories together. But I don't, I mean, some of them might help me, and some of them might be like, just like that, you know, just very small, but I don't count them in my local uniqueness event, okay? I really can't, I'm really only asking, are all the trajectories that are inside this ball of size r, are they all connected together in a twice bigger ball? So just to give you a proper definition, let me write this event. So the local uniqueness event, so it depends on the parameter of your interlacement of x will be the center of your ball here. Okay, and so this is just means that for any yz in your interlacement set, which are in your ball of size r, you want that there is a path from y to z in your interlacement, and more precisely in the restriction of your interlacement to the ball of size 2r. Okay. So this is one way to see it. Another way to see it is to interpret it is to think about the approach of random interlacement as a limit of a random walk on a torus. So if you remember, right, what I was saying, that what I could do to observe my random interlacement is just to run a random walk on a much bigger torus than my R here. And then just look at the excursion of my random walk, which hit my ball of size R. And the question that you're interested in is, okay, are all these excursions of my random walk connected together locally or not? This is another way to phrase the question. And so the first one to study this question were Raf and Sapochnikov, still in the same paper. So 2011. And I will just focus, I mean, there are further results on overgraph, but I will just focus for simplicity on the case of ZD. And that theorem tells you that the probability of this event goes to 1, and it goes to 1 actually very fast. So it goes to one stretch exponentially. Maybe let me take that CR to the C bar. And this is true for all U positive and maybe R larger than C. And let me mention, so this constant here, this is a constant that depends on U. And when U is small, it becomes harder to have local uniqueness because you have just a few trajectories. Okay? So when you have a few trajectories, it's not clear if they will indeed connect each other, especially in high dimension. And this constant here is, however, a constant that only depends on the dimension. I mean, they all depend on the dimension implicitly, my constant, but this one does not depend on it. That's my point. Right. Is the statement clear? So, before going into the proof, let me just give first some motivation on why this kind of statement is interesting and what can you do with it. So the first one will be about percolation in slabs. So let's say you want to show that the interlacement percolates on Z2. So it will be hard. So let's say you want to do it on a slab. So Z2 times 0R to the D-1. So what you do is, okay, let's say you have the whole plane. This is really big. And then you take certain number of points. Like this will be R over 2 ZD, if you want. These points. So what this means that the distance between these 2 points is R over 2. Okay? And let's say you have a certain path inside your R over 2 ZD here, your renormalized lattice. So let's say you have x1, x2, x3, x4, x5, x6, x7, x8, x9, something like that. You fix a path, like, okay, it's given to you. And let's say you're on the event that for all E smaller than n, where n will be 9 for us, but it's general, you know that you have local uniqueness around each of the xi. Okay? So I will ask for local uniqueness, and I will ask for slightly more. I will ask also that there are trajectories, because in the local uniqueness event would be true if there's just no trajectory in the ball of size R, but then it's not very interesting. Right? So I will ask additionally that the interlacement indeed hit my ball, and more precisely my ball of size R over 2. Okay? So if this event occurs, then what do I know? I know that each of the xi has some random interlacement trajectory next to it, okay, at distance at most R over 2, so like that. This is the first thing. And the second thing is that I know that there is local uniqueness, and since here the distance is R over 2, the local uniqueness event tells me that these two trajectories must be connected together. Okay? So I know that I can find a path like that that goes from here to here. Maybe it's made of multiple trajectories. I don't know that. I don't know how many trajectories there are, but I find a path. Maybe it's this one that continues. And I can connect like that all my neighbors. Okay? So what I've just constructed here is basically under this event a path from left to right, if you want. And more generally, it's like, okay, let's say you just have a few. So the probability of local uniqueness is really high, okay, if you take R large enough, depending on. And let's say, okay, you just have a few points where your local uniqueness do not happen because it's a very rare event that it does not happen. So maybe you have this point here that you need to remove, this point that you need to remove, and this point. Okay? So these points are such that here is like no local uniqueness. Or no trajectories. I mean, that this event here does not happen. but this is also really unlikely that there is no trajectories, because the probability of this event, if you remember, this is 1 minus exponential minus u times the capacity of this ball, so this is also stretch exponential. So everything is really likely. Here you see that, okay, typically I have only a few boxes here where I don't have local uniqueness, and so what this means is that if I have a path from left to right, for instance, where I have local uniqueness, like my path here, then I've been able to find a path from left to right. And more generally, as long as I don't have a blocking surface of, an infinite blocking surface of purple here, then I will be able to find an infinite path of my interlacement which follow my non-purple boxes. Okay? So what you can show with that is that, I mean, this is the answer just intuitively, IU intersection with a ball around Z2 of size R percolates. So more precisely, for all U where exists R such that this true. Okay, so what you need to show this ends is that the probability to have a long path of purple set here where you don't have local uniqueness is very small. So you don't have independence, so you need to work a bit more. But I'm not going to go even to that. Okay, it's very unlikely event, so they will not percolate. Okay, so this is the first application. Another application is stability to noise. And this is Raf Sapochnikov 13. And what is stability to noise? This just means that for every U, you can find a Bernoulli noise. So this is Bernoulli, a Bernoulli percolation model, if you want, with parameter P. Okay, so there exists P first, such that if I take BP intersection with IU, this still percolates. And BP is my Bernoulli percolation model with parameter P. Okay, so even if I add some noise to my interlacement, I remove a few points from it at random, okay, then I still percolate. So this is, if you were doing just one trajectory, this would be much harder, because if you remove one point of the trajectory, it has a good chance of disconnecting it. But here, the fact that you have multiple trajectories in your interlacement is helping you. And so why is that? Well, you just come back to the picture above. And you add one more color. So what you do is you say, okay, but maybe there are some sets, some X, such that the ball around it here contains, so the ball contains a point in my Bernoulli set. Okay, if somewhere here I have a point, there's a point which is not in my Bernoulli. So if somewhere there's a point which is not in my Bernoulli, I remove it from the picture. So if P is really large, this is unlikely. So P is really large compared to R. You fix R is fixed, okay, and you make P goes to 1. Then this is very unlikely that this happens, but this might happen at a few places. Okay, maybe it even happens here, so you need to remove this point, but it doesn't matter, huh? As long as you don't have too many of them, you can still find like a path like that from left to right, or an infinite path, as long as this purple plus brown does not percolate, basically. Okay, and you're still able to find infinite paths. That's the idea behind this theorem. So it's, in general, it's an event when we can control it nicely, as we can here, which is very useful whenever you try to do some percolation argument in the supercritical regime. And I mean, since the interlacement is always supercritical, it's very useful to study interlacements. So there have been other applications where we are not going to the detail of why you can use it, but maybe you can try to think about it. Since then, so one of them is also the transients of the interlacement. So if you run a random walk just on your interlacement, then this random walk is transient. And this is actually to prove this theorem that they first introduced this event. Just basically because it's everywhere enough, and there's only a few places that are missing, and so that's why you can get transients. And another result is that each two trajectories of IU are connected by at most d/2 trajectories. So what this means, for instance, in dimension 3, is that every two trajectories of the interlacement are connected together. But in higher dimension, it's not necessarily true. You might need to use one additional trajectory in dimension 5, for instance, and in higher dimension, you need to actually to connect two trajectories together. You need to actually use multiple trajectories. And okay, this is not directly a consequence of the local uniqueness event, but it's more a consequence of the proof of the local uniqueness. Okay. All right. So this is some motivation. We'll see more later, more application later, but I'll stop here for the moment. I forgot to say this was Raf and Sapochnikov. In 12. But now I want to explain the proof, which is relatively easy to explain. I mean, it's relatively to explain in low dimension. I will only explain the proof until dimension 5, not give the proof in higher dimension. Because it's easier for the random walk to intersect each other in low dimension, right, than in high dimension. So, okay, let me maybe first do a drawing to explain what is the proof strategy, and then see how we can apply it. So you have your ball of size r, okay, and you take 2 points, x and y, in your ball, and you want to connect them together. So what you know is that these are points of my interlacement, so this means they are part of some trajectory, both of them. So you have some trajectory here, okay, and this one I will call x, and this one I will call x, y. Okay, so for both of them have some trajectory of interlacement connected to them, and the strategy is to say, okay, I have this trajectory of interlacement, but this trajectory of interlacement, it has a big capacity using my large deviation bound here on the capacity. Okay, so I know that the capacity of this trajectory is big, and since it's big, it means by definition of random interlacement is that there are many random interlacement trajectories that hit this green path here. Okay, so I can actually draw many trajectories here that from my interlacement that will hit this green path. And the question is, okay, if you didn't have local uniqueness, it means that each of these trajectories would fail to hit my path here on the right? This would be what happens if you don't have local uniqueness, but this is really unlikely because you have many trajectories, and one of them at some point will manage to hit the green on the right. Right? So that's the idea. Okay. So, well, what you can say is that with probability 1 minus exponential minus t minus c, the capacity of xx, maybe let me call them xxr, this is their run until they exit the ball of size r, or 2r more precisely, because x could be just close to here. But, so I know that this will be larger than TF of R, and the same result is true for X R, Y. Okay. And so now, maybe go somewhere else. Let me keep the theorem that we're using. But now, let me define, so what this means is that there are more than u t f of r. So remember the number of trajectories that hit this green path here. This is u times the capacity. It's Poisson with parameter u times the capacity. So okay, here I'm asking that my Poisson variable is maybe not larger than its mean, but larger than half of its mean, and this would be a really likely event. I can afford that. Trajectories of IU hitting X, R, X. Okay. With high probability, the same kind of probability as well. Okay. And so now my local uniqueness event, or is the complement of my local uniqueness event. Let's say U X UXR. Complement. This is smaller than, so this is smaller than the probability that all of these trajectories fail to hit my green path here. Okay, so this is smaller than the supremum over all z in the R. So this is the starting point of my trajectories of the probability that the drawn walk here do not hit the green one. For any of my trajectory, so this is to the power a half UTR plus some exponential minus T minus. Okay, this is the event. Okay, and so how do I compute my probability to avoid my walk? Well, as usual, I use the fact that the probability to hit the walk is related to the capacity, right, by this heating formula from last time. So, yeah, I would need that's a sum over x, y. I mean, okay, this is not the same. Let's do it on 0. You might have a r to the, but since this would be exponential, it doesn't matter. And so this probability, or 1 minus this probability, this is of order the capacity of x, r, y. Or, I mean, this capacity, we know what it is. Let me just replace it immediately. We know that it's Tf of r with high probability. Right. Divided by the green function, and the green function I can always bound it by r to the d minus 2 because I'm inside my ball of size r. Okay, to the power of half UTR plus my exponential error, which is fine. And so, sorry, this is not an R, this is an F of R. This is my capacity of my first. And so now, typically, this is smaller, if you remember what F of R is from the left, and T is also small, so this you can write as exponential minus this. Right, and so this is R to the 2D exponential. So, I mean, I guess there's not an extra parenthesis here. Remove that. So you get what? You get exponential minus some constant, because there are some constant here too. U t square. Maybe let me write it first. U f of r square t square. R to the 2 minus d. Okay, and now comes the question of what do I choose for t, because t is the parameter that I'm free to choose. and you want typically to take it polynomial, because you want at the end that to get a stretch exponential decay, so you want your second probability here to be at least stretch exponential, right? And so then you have different cases. Let's first focus on the case d equal 3. So in the case d equal 3, f of r is just equal to r. Okay, so with d equal 3, this here, this is just r to the 4 minus d. Okay, and I mean if times t squared. Okay, and r to the 4 minus d in the dimension 3 is just r. Okay, so this is really stretch exponential, and I can, for instance, take t equal u f of r to the minus 1 over 6. Okay, and if I do that and I plug this in my my computation over there, I will get, and there's an r to the 2d, which doesn't matter, but I will get exponential minus c ur to the c. So this is just ur in dimension 6, dimension 3. And so this gives me indeed an exponential minus ur. And here you need to check that, okay, the u and the r, they have the same power actually, but you can check that easily. This gives you this 3. All right. So then in dimension 4 and 5, I can take the same t. But what happens is, let's say, so in dimension 4 and 5, typically f of r is of order r squared. Okay, so here I will get like an r to the 6 minus d. And 6 minus d is positive in dimension 4 and 5. Okay, so then the same bond will give me an exponential minus, so this constant does not depend on u. It's independent of u. There's some constant of u now, but I will not write explicitly. You could do it, but I will not do it because it's not optimal. Then the reason why I write it in dimension 3 is because it's optimal. And it's almost optimal in dimension 4. You will have some log discrepancy, but not going into detail. And this works well. This gives you still the result that you wanted. Now in higher dimension it does not work anymore, because then you get still this r to the 6 minus d here, which then will go to 0, especially with the t square in front. And then you need to work more. So I'm not going to do this, but just to give you an idea of what happens in high dimension. So in high dimension, this might fail. This is what we just got. Okay, indeed, all my red trajectory might all avoid my green trajectory just because they live in far away and in a completely different dimension, right? And so what you do is you just say, okay, but the capacity of all my red trajectory here, it's much bigger than the capacity of just my green trajectory here. So I can also look at all my interlacement trajectory that hit my red one here. Okay? And I have one interlacement trajectory like that, for instance, and I just need one of them to hit my second green one here, and this will happen likely, okay, until dimension 8, and then you need to reiterate that to get in, the result in high dimension. Okay? But just as a remark, I proved a slightly, I removed it, yeah, I guess I removed it. But as a remark, I proved a slightly stronger result in dimension 3. I proved, I got actually the correct dependency on u, which will turn out to be correct. That is in dimension 3, I got local uniqueness, and here my dependency between u and r will be u times r. And we will see later that this is actually what one should expect by showing a matching lower bound for, you need to change this constant here and so on, but almost matching lower bound for this exponential. All right. Yeah, I will stop here and we'll see tomorrow how to use this local uniqueness events to get some information also on the Gaussian field. Thank you.
Some questions?
why it was important to understand precisely the dependency.
Yeah, so this will be important more tomorrow. I mean, it's basically it's you know if you're interested, this is like some kind of critical scale, if you want, where the local uniqueness starts to kick in. So basically, the question is, if you look here and you try to make these kind of pictures, exactly what is the size? If U is small, okay, which will be typically the case for us, what is the size of the boxes that appear here? And so in which slab do you percolate, in a sense? And these boxes here, I see that they are of order 1 over U. Okay, so this is also true for my second event, for my event that IU intersects the ball of radius R. And so in generally, in all dimensions more than 6, you expect that this is 1 over U to the 1 over d minus 2, which is just 1 over U in dimension 3. And this will be important to know exactly, precisely how big all these boxes here are.
What's roughly the idea to prove this first result with stretch exponential decay for local uniqueness? I would have thought it was a reasoning like the one on the left.
To prove what, sorry?
The stretch exponential decay for non-local uniqueness. I would have thought that we could.
Yeah, but I mean, this is what I put. I mean, this is what I'm looking at the complaint, and this is what I get the stretch exponential.
One quick question. Do you know the optimal constancy that you can put?
You mean here?
No,
I mean in the theorem?
In the stretch exponential decay. Like the power C prime.
Power C prime, yes. So this depends on this one. Okay.
But you have a conjecture but optimal.
Yeah, so this should be 1 in dimension larger than 4. And in dimension 3, actually, this should be UR over log of UR. I mean, this is theorem. It says UR over log of UR in dimension 3, and it should be, and it's not the same power of U, the power of U depends a bit on the dimension, but it should be 1, the C prime.
Okay, so if no other questions, ça clarifie bien.